Magnetic resonance spectroscopy has a problem: too much data. This technique excites atoms in the magnetic field and records their radio emissions, which is a sum of decaying sine waves, and then determines what chemical compounds are there by examining the decay rates and the frequency of those sine waves. In the lab, there's no problem, but when you look at a human body, there's so many different compounds there that tens of thousands of measurements are required. The problem is that existing algorithms cannot handle this amount of data. For example, if you wanted to analyze 1,000 measurements, a reasonable implementation on a modern computer would take about a second. 10,000 measurements would take about an hour, and 1 million measurements would take 100 years. I have developed an algorithm that works much faster, n log n operations versus n cubed. Although slower for 1,000 measurements, analyzing millions of measurements takes seconds, not hundreds of years. My technique is based on a simple idea. Not all those million measurements are really necessary. By carefully combining the raw measurements, I can determine a smaller set of measurements that I use to determine the frequencies and decay rates. The key is choosing the right combinations of these measurements, but I have found a way that gives accuracy, that gives answers with almost as accurate as solving the full problem. Would you be okay with sacrificing a bit of accuracy to solve a problem in seconds instead of years? I am. This is a powerful result because combinations of sine waves appear everywhere in signal processing, sonar and radar to name a few. Now that we can exploit large amounts of data efficiently, we can expect faster answers to many problems.
Charles Peltz.
Okay, I'd like to start off with 3 ideas: random, periodic, and electronic. There's a fundamental difference between electronic properties of periodic and random structures. Nobel Prize winning work has led to the main result that electrons move well in periodic structures and not well at all in random ones. This is really crucial in providing insight into the building blocks of our universe and in developing technology relying on quantum transport. I'm interested in building on this work by investigating the intermediate region between periodic and random. So I study a model of a quasi-crystal, an object appearing in nature and possessing structure that lies in this intermediate regime. Quasi-crystals have gained relevance from the work of a 2011 Nobel laureate and have some critical applications. For example, steel tools used in surgery. It turns out the energy levels of this quasi-crystal model I studied range in exponentially small fractal patterns that tell us about electron transport. So I developed an algorithm to compute these levels. A good approximation to these fractals require calculations with huge matrices of size 500,000 at least. So this algorithm is efficient and highly accurate. These calculations handle some of the largest matrices anyone's ever used. This work will illuminate the intermediate regime and provide a tool to push forward the boundary of knowledge of our physical world.
Jizhou Li.
58% of the entire original oil reserve in the U.S. was trapped in the discovered reservoir, but was labeled as unrecoverable by current technology. With this staggering percentage and increasing energy demand, engineers have come up with a highly effective enhanced oil recovery process. Instead of using water, we inject solvent into the reservoir to mix with the remaining oil and eventually be forced out of the reservoir. This process is governed by a system of mathematical equations. My job as a mathematician is to design a robust numerical method to solve the equations and produce high-resolution imaging for the recovery process. One of the biggest challenges I've been facing with is to incorporate the sophisticated rock formation in the reservoir and solvent properties that in order to provide the high-resolution imaging in the oil recovery process. When I'm finished with this method, they will have a capacity of handling different types of reservoir as well as solvent. And for engineers to design and optimize the recovery process. And we'll get that 58% of oil out there. Thank you.
Yan Huang.
To find the oil and gas, we need to understand the structure of the Earth. But the Earth is not transparent to vision, so we cannot see through it. In seismic survey, geophysicists hit the ground to generate sound waves. Those sound waves travel through the rock deep into the earth. When those sound waves meet a subsurface structures such as the contact surface between oil and gas-saturated rock, part of it will be transmitted and travel deeper, part will be reflected, travel back toward the surface and heard by us. Those reflected waves carry some information about the subsurface of the earth, so we cannot see through the earth, but the earth can talk to us. Isn't that amazing? The next question we ask is, if the earth talks to us, can we necessarily hear it? So if part of the sound generated in the seismic survey travel back toward the surface, will it reach us? My work explores the condition of the mathematical model of the Earth that guarantees the arrival of some of the sound, so that when the Earth talks to us, we can hear it. Thank you.
Megan Whaley.
When I say go, I'd like each and every one of you to say aloud what the capital of Texas is. Ready? Go.
Austin.
Believe it or not, your thought process made several stops along the way toward reaching that final answer. From processing my voice to deciding on the response and finally articulating that response. Now pretend part of your skull had been removed and electrodes were implanted directly on your brain's surface, recording its electrical activity every single millisecond as you were going through that thought process. Intracranial electrode recordings are so precise that they're used to localize seizures in epilepsy patients. The goal of my research is to use these recordings to determine how and where language lives in the brain. I'm working with hundreds of these intracranial electrode recordings taken from human subjects while they participated in a language task. By building on an existing model, I developed a new way to illustrate directionality and magnitude of influences occurring between brain regions. My method is groundbreaking because it aggregates significantly more data relative to other modern studies in this field. The graphical representations generated by my model can be used by neurosurgeons to more accurately identify the location of brain regions that are crucial for language and thus take special care to avoid them during medical procedures. Thank you.
Do you know why gas is so expensive right now? One main reason is that oil companies are only able to produce 1/3 of the oil from reservoir. So how about the 2/3? They cannot find it? They cannot produce it? Yes, they cannot. But why? Because of the inaccurate numerical method they are using. Today I'm going to provide solutions which can make millions of dollars each year for you. And one of the methods to produce oil is to inject gas or water to displace oil in the earth. Therefore, the prediction of the fluid flow is crucial. However, the rock properties are randomly distributed in the earth and it is really hard to find it. But oil companies are trying to find it and identify it by only grabbing the rock samples whose volume is less than 1% of the volume of a whole reservoir. Can you imagine the significant uncertainty in producing oil? I can. And of course, I apply one of the most important and most of the advanced method to capture and identify the property of the rock. And meanwhile, I have already developed a method which is able to capture more than 95% of the fluid flow in the earth accurately by comparing with the benchmark result. And amazingly, the computing time is reduced by 80%. Cheap, elegant, amazing. That is my solution to oil production. Thank you very much.